Hey, AP Chem. We're going to finish chapter 10 today. Basically, we want to talk through phase diagrams, and then I want to touch base on a couple different forms of solids and some applications that come out of those forms of solids. So in order to get to phase diagrams, I want to revisit some of these concepts we've talked about before and tie them to intermolecular forces. So the first topic that we want to do this with is vapor pressure. Let's look at vapor pressure again and talk about how vapor pressure ties in with intermolecular forces. So you may recall that vapor pressure is a pressure that is established in a closed container when you have a liquid or a solution, and above that solution is a vacuum. Okay, so when that occurs, some of the particles, remember these liquid particles are constantly in motion. They're bouncing off each other, they're bouncing off their container walls, they're bouncing off the surface, and if they strike the surface with enough energy, those molecules can actually escape into that vacuum, and they're going to establish a pressure up there. So once we have a specific amount of molecules that have escaped their solution, then those molecules in the gas phase are now bouncing off the walls of their container, bouncing off each other, bouncing off the surface. Some of them re-enter the surface. And when that rate of escape is equal to the rate of re-entry, then the pressure that has been established by that gas is going to be called vapor pressure. And this happens naturally. If you're given a container of water at a specific temperature, then it will consistently establish a vapor pressure. You can actually look that up. So at 25 degrees Celsius, what's the vapor pressure of water going to be? At 30 degrees Celsius, what's the vapor pressure of water going to be? And as the temperature changes, the molecules are going to be more energetic, right? And more vapor pressure is going to be established above the surface. As temperature gets dropped, those molecules are going to move more slowly, be less energetic. You're going to have less escape. The vapor pressure is going to be lowered. Okay, so let's think about this in terms of intermolecular forces. So as that liquid is trying to escape into the gas phase, what kind of intermolecular forces are present? Well, that depends on what the solution is, right? If the solution is hexane, which is a nonpolar molecule, then the intermolecular forces that need to be overcome in order to escape the solution into the gas phase, for something that's nonpolar like hexane, the intermolecular forces are going to be London dispersion forces, and London dispersion forces only. And so hexane tends to be fairly volatile. A volatile solution is a solution that establishes vapor pressure very easily. It escapes out of the liquid into the gas phase easily. If the molecule has a scent, has an odor, you're going to smell that odor very quickly. A good example of this is ammonia. Ammonia is very strong smelling. It's also extremely volatile. And so as soon as you uncap either ammonia crystals or a solution of ammonia, you're going to smell that ammonia really, really quickly. Because it's an extremely volatile compound. Well, hexane's the same thing. Hexane is going to escape pretty quickly out of its liquid form, and if you don't keep the cap on that solution, you're not going to have a solution after a couple minutes, a couple hours, depending on how big your container is. You're going to have hexane vapor all over the place. Which is kind of dangerous because hexane vapor is flammable, and you don't want a flammable vapor hanging out in certain corners of your room without you knowing about it. So Returning to our solution, if the solution is polar, on the other hand, like water, for example, then the intermolecular forces that are holding the water molecules together are going to be dipole forces. And in the case of water, you're going to have hydrogen bonding dipole forces. Those are pretty strong forces. And so the water is going to have quite a bit of energy or quite a bit of a push towards disorder in order to actually escape. And the vapor pressure that gets established is going to be lower. If you compare the vapor pressure of H2O, which has hydrogen bonding dipole forces, and H2S, which has only dipole forces, not hydrogen bonding dipole forces. H2S is probably going to have a higher vapor pressure because it has weaker intermolecular forces. Now, we talked about vapor pressure as a colligative property, right? And a colligative property is something that changes based on the number that's present, not necessarily the item that's present, right? So if we think about vapor pressure as a colligative property, that is the case where we take something that will dissolve, whether that's sodium chloride, which dissolves into 2 ions, right? Or that's something like sugar, which dissolves into 1 molecule. If we put something in here with our water, that's going to dissolve. We now have another interaction in that water. In the case of sugar, you're going to have another dipole attraction in there. In the case of salt, what you would have is an ion dipole intermolecular force happening here. And do you recall what happens to vapor pressure when you put a non-volatile solute in there? Vapor pressure decreases, right? And there is a law for that. For vapor pressure, it is Raoult's law, right? Where you have the vapor pressure of the solution equals the mole fraction. Actually, let me give this instead of an S. Let's give it an A. The vapor pressure of whatever you're looking at is going to be equal to the mole fraction of that thing that you're looking at times the vapor pressure initially. So I forget how we indicated that, something like this. So that's the vapor pressure of the solvent that's present without the solute in it currently. So notice that the mole fraction, so moles of whatever you're looking at over moles total, is going to affect the vapor pressure, and it's going to bring the vapor pressure down by a certain fraction, right? Whatever that fraction is. The vapor pressure with the solute is going to be lower than the vapor pressure with no solute. Okay, so vapor pressure is affected by intermolecular forces. The stronger the intermolecular forces, the lower the vapor pressure is going to be. This is just a recap on the definition of vapor pressure. If you want to pause the video and read through this, you can. It should be review based on what we've talked about before. Now, vapor pressure, in addition to being affected by intermolecular forces, we talked about how it's also affected by temperature, right? Because the kinetic energy that is indicated by temperature change is going to work against the intermolecular forces. Intermolecular forces tend to hold things together, therefore decreasing vapor pressure. Temperature tends to break those things apart, or kinetic energy tends to break those things apart, therefore increasing vapor pressure. Well, we have another factor here, and that is atmospheric pressure. And atmospheric pressure works in conjunction with intermolecular forces. So intermolecular forces tend to hold things together and decrease vapor pressure. Well, so does atmospheric pressure. The more atmospheric pressure you put on something, the closer you're going to push those molecules together, and the stronger those intermolecular forces can be. And we see this when we look at a solution. This little bowl of kumquats is supposed to be a solution, by the way, a solution at STP, so maybe ocean level, versus that solution on a mountaintop. So this is a difference in atmospheric pressure. If you're at ocean level, you have this entire column, this entire altitude of molecules that you're under. If you are on top of a mountain, right, you kind of skip. You climb up the mountain and you climb past that original column of molecules pushing down on you. Remember, these molecules are being pulled down by gravity. And so they are being pulled down on your shoulders, on your head, on your hand, on your cup of coffee, right? And they are pushing the molecules in the solution closer together. If I had coffee in here, this would be a better example. Okay, they're pushing the molecules of my coffee closer together, and those molecules can therefore experience their intermolecular forces a little bit more strongly and decrease the vapor pressure. Well, when you climb past that column of molecules and you're on top of a mountain, you actually have a smaller column of atmospheric molecules pushing down on you, pushing down on your solution. And so those intermolecular forces can be overcome a little bit more easily. So atmospheric pressure is less, the vapor pressure can overcome the atmospheric pressure a little bit more easily, break those intermolecular forces, and you have more of a vapor pressure. That actually affects your boiling point. So the boiling point is the point at which your atmospheric pressure is equal to that force causing the vapor pressure, and the liquid starts to turn into gas. That's boiling, right? Liquid turns into gas and escapes the body of liquid. Well, when atmospheric pressure is equal to the vapor pressure, boiling occurs. So if we reduce this pressure above our solution, then we're decreasing the atmospheric pressure, and we're going to actually change the boiling point. And this is why when you buy a cake mix or something like that, and you look at the directions that are on the back, they'll have directions, and then at the bottom it'll say if you are above an altitude of 1,000 feet, here are your baking directions, right? You actually need different baking directions because your boiling point is going to change because of this difference in atmospheric pressure. That is now allowing intermolecular forces to be overcome and molecules to escape the liquid phase into the gas phase more easily. And that's what we call vapor pressure. Okay, so intermolecular forces make a difference. Temperature makes a difference because that affects kinetic energy. And then pressure makes a difference because that influences the atmospheric pressure and the vapor pressure. It influences that interaction that the intermolecular forces can have. Okay, here's a little diagram just showing you this exact same concept in arrows. So in the first arrow, we have vapor pressure, which is our up arrow. So this is our solution trying to escape. So vapor pressure is bigger than atmospheric pressure. Boiling is going to occur here. Here, where they're equal, you are at the boiling point. So you are at the point where boiling can occur. And then if the atmospheric pressure is bigger than the vapor pressure, then this is not boiling. And again, we can see this in terms of atmospheric pressure. If your boiling point is at 1 atmosphere, then below 1 atmosphere of atmospheric pressure, boiling can occur. Above 1 atmosphere of atmospheric pressure, boiling cannot occur unless you change the temperature. Okay, so we have a pressure effect, we have a temperature effect. Okay, this is the same idea shown to you with a barometer. This is the same idea shown to you in terms of like a particle representation. If you want to pause the video and think about this, you can. This is the same idea communicated through a manometer. So here we're kind of cycling back through these like our solutions chapter where we talked about colligative properties. We're cycling back through our gases chapter where we talked about barometers and manometers and vapor pressure in gases. Okay, so this brings us to a definition of a normal boiling point. So this term normal actually indicates a specific pressure. So normal indicates a pressure of an atmospheric pressure of 1 atmosphere. So this is used to compare certain solutions, because if you say, oh, what's the vapor pressure, what's the boiling point of water and carbon dioxide, but you communicate water at 1 atmosphere and you communicate carbon dioxide under this extraordinary amount of pressure, it's not a very useful comparison, right? That's why a lot of times at STP just gets tacked on to the end of problems. Not that they expect you to do anything with this idea of the fact that it's at a STP, just to show you that the comparisons can actually be made on a level playing field. So that's what this term normal says. Normal indicates that your pressure is 1 atmosphere. And therefore, you can communicate these comparisons a little bit more easily. Okay, so here's a graph that you may see. This is a graph of vapor pressure curves, and you can see here that it's communicated in terms of pressure versus temperature. Okay, and then for specific things like water or ethanol or diethyl ether, you can see how the vapor pressure is going to change at specific temperatures and specific pressures. And then you can see here what the normal boiling point is. So you have a normal boiling point line. So this is at 1 atmosphere of pressure, which is equal to 760 torr, or 760 millimeters of mercury. So at this normal of 1 atmosphere, what is the vapor pressure of these things? And at what temperatures do they occur? So on the test, if they were to give you this graph, they would expect you to be able to just read information off of this graph, be able to interpret it. If they give you a specific temperature, you should be able to tell me what the vapor pressure would be at that temperature. And you could do some comparisons between water and ethanol. For example, notice that the normal boiling point at 1 atmosphere for ethanol is somewhere around 75. The normal boiling point for water at 1 atmosphere is somewhere around 100. That has implications for distilling, right? We could bring the temperature up to 80 degrees Celsius and boil off ethanol, but the water in our solution wouldn't actually boil yet. It wouldn't be at the boiling point for water. So it has implications for things like physical means of separating mixtures like distillation. Okay, here's a practice we'll do together. This is just a return to our heating curve. It's labeled a little bit more better. It's labeled better than our last one was, but it communicates the exact same information. Okay, so now we get into phase diagrams. So this is what a phase diagram looks like. So a phase diagram communicates the three phases, right? Solids, liquids, and gas. And there's a whole bunch of interesting information all packed into one graph. So let's go through that information while we're looking at the graph, and then we'll return to that page before so that if you want any like written definitions, you can get them off of that page. So a couple things that you should be able to see or read or notice off of this graph. First of all, solids, liquids, and gases are always in very consistent places. So notice as temperature increases, if we pick a line of pressure, we usually go through solid, then liquid, then gas. There's a couple points which we don't. We go straight from a solid to a gas, and that depends on the pressure that we look at. But usually we're going to go through solid, liquid, and gas. Now, that is helpful information to know because a lot of times when they give you these phase diagrams on the AP test, they don't actually label which section is a solid, a liquid, or a gas. That's a favorite question that they like to ask you. So they don't actually give you these labels, and they expect you to be able to come up with those labels on your own. And so thinking of it in terms of a temperature change across one pressure is usually the most helpful way to do it. Okay, other interesting things on this graph. Okay, you have lines here, and the lines communicate phase changes. So notice you have a line here, and it's the barrier between your liquid and your gas, which means that depending on which way you're going, liquid to gas would be condensation, gas to liquid would be vaporization. You could do that horizontally at a consistent pressure. You can also do that vertically at a consistent temperature when you're changing pressure. So if we go from a high pressure to a low pressure, you're going to get condensation at a specific temperature. If you go low pressure to high pressure at a specific temperature, you're going to get vaporization that occurs. Same thing with solids and liquids. We have a line here, and that is the fusion barrier. So that's the barrier at which melting and freezing is going to occur. Again, these arrows are showing it to you at a consistent pressure going from a low to a high temperature. You can also go vertically from a high pressure to a low pressure, but that one, there's not as much room to maneuver. And we'll actually return to that idea in just a second. Okay, and then this line is going to be the sublimation deposition phase change line all around there. So straight from a solid to a gas, skipping liquid entirely. Okay, so those are your lines. Now you also have some interesting points. So first of all, any point on this line, like if I give you point C or point D, you should be able to tell me what phase change is happening. Outside of those points, you have two other points that are noteworthy. First of all, you have a triple point here. This triple point occurs at a very specific temperature and a very specific pressure for whatever whatever substance you're looking at, and that is the point at which solids, liquids, and gases are all present at the same time. It's kind of a cool idea. There's some interesting YouTube videos about that. Okay, this point B up here is called the critical point, and beyond the critical point is this hazy area where it looks like the color has been accidentally erased, but that is purposeful because above this critical point, you get this area where liquids and gases are indistinguishable from one another. It's a fluid, but we're not quite sure if it's a liquid or a gas. And up here is kind of where we get into the idea of like plasma. So critical point, triple point, you have all the line barriers. Okay, let's go back and see if we missed any of these. All right, so we talked about the triple point. We talked about the vapor pressure curve, the critical point, the melting point. Okay, normal melting point. If you are given a phase diagram, and you can find 1 atmosphere pressure. Notice on here we can't find 1 atmosphere pressure, but a lot of times what they'll do is they'll draw a line here straight across, and that will be your normal, also known as 1 atmosphere of pressure. And so you can find the boiling point by going from that normal on the liquid gas line and figuring out what temperature that occurs at. Or you could find your normal point of fusion, for example. So a lot of times you'll see those indicated on your graph as well. Okay, now another interesting comparison that they like to do is the difference between water and carbon dioxide. And again, instead of going through all of these words, I want to look at the diagram itself. So there's a lot of differences between the water diagram and the carbon dioxide diagram. Notice the triple point exists at a different point in time. Are different temperatures and pressures. The critical point exists at different temperatures and pressures. The solids, liquids, and water, they take up different areas and they have different shapes. But possibly the most interesting difference between these two graphs is this line right here between the solids and the liquids. Notice that in carbon dioxide, the slope is positive, and in water, the slope is negative. And that is interesting because as you raise pressure for water, well, let's start with carbon dioxide. As you raise the pressure in carbon dioxide, look what happens to the phases. So we start in a gas, we raise pressure, which should cause condensing to occur, right? I may not have drawn that in the right area, but okay, we raise, nope, I gotta go over a little bit. Okay, we raise pressure and our gas becomes a liquid, and then our liquid becomes a solid, right? That makes sense. If we hold the temperature constant, gas gets pushed close together, becomes a liquid, gets pushed close together, becomes a solid, right? And that's what happens with carbon dioxide. Well, look what happens with water. If I draw the line in the right spot. At a specific temperature, my gas, as you raise pressure, becomes a solid, and then the solid becomes a liquid. And so what this is saying is the most condensed phase for water is actually liquid, not solid. And this is what we talked about before with hydrogen bonding, right? As water freezes, it actually expands and more space gets put in between molecules as those very strong, influential hydrogen bonds find their perfect distance and angle and lock ice into place. It actually expands, which is unusual for solutions. Water is one of the only things that does this. Most things actually condense as you exert pressure on them, and they move into their condensed phase. So that's probably the most interesting part of the difference between these two diagrams. They may ask you about that on the test. Phase diagrams has not been high on their list for a couple years, so who knows if they will ask you about that. Okay, and this gets to our final topic in chapter 10. we've talked about intermolecular forces and how they influence the phases, solids, liquids, and gases. Now we just want to spend a little bit of time talking about different types of solids. So this graph has a lot of information on it, but most of the information on it is examples. So let's break it down just a little bit. First of all, when we're looking at solids, there's really 3 types of solids. There's a crystalline ionic solid, there's a molecular solid, and there's an atomic solid. And the difference between these solids is what is at the point in the lattice. Remember that anytime a solid is formed, it's formed in terms of a lattice, right? And that lattice can get super complicated, but the question of what type of solid forms is going to be what is at the point in the lattice. So for an ionic solid, the thing that's at the point in the lattice is an ion. An example of that would be sodium chloride. In a molecular solid, the thing that's at the point in your lattice is actually a molecule, like H2O could be at one point in your lattice. This whole thing would be H2O, or carbon dioxide. And you can see a whole bunch of examples here. Sugars in there, phosphorus, sulfur, iodine are in there. And the thing that is doing the attracting between these molecules is actually not a bonding force. It's either a dipole-dipole force or London dispersion force. If we look at ionic solids, the thing that is doing the bonding in between our points in our lattice is actually an ionic bond. And so we can see here now why solid water, solid carbon dioxide, things like this would have a lower melting point, lower boiling point, because the forces holding the solid together are not as strong. Why can you melt sugar on the stove, but you can't melt a rock? You can't melt salt on the stove, right? And this is why, because in order to melt that salt, you have to overcome the ionic, directional ionic forces, which is going to be much stronger than overcoming the dipole-dipole force that's holding sugar molecules to other sugar molecules in the sugar crystal. A third type of solid is going to be atomic solid. So at the points in the lattice, you actually have atoms. Carbon, different forms of carbon fall into this, different forms of silicon. And you can see there's 3 subgroups that fall under this. There's a network solid, a metallic solid, and a group 8 solid. And all of these have atoms at the point in their lattice. So some of these, like the group 8 solids, anything that has a noble gas at each point in the lattice, it's going to be held together by London dispersion forces. It's not going to be a super strong bond. These molecules are going to fall apart very easily, and they're going to be overcome by kinetic energy very easily too. Metallic solids fall into this. Any solid that has a metal at this point in the crystal, like aluminum or mercury or copper, what the forces holding the solid together are going to be delocalized, non-directional covalent bonding. So this is like with metals. Aluminum's a favorite example here. Okay, so aluminum looks something like this. Okay, for metals, what they do is they actually give up these valence electrons to the group. And so you get these cations, right? If aluminum loses 3 valence electrons, it's now going to be a 3+ charge. So you get these cations at the point in each lattice. And you get this sea of electrons that has been given up and is able to flow back and forth over this crystalline structure. And it gives them really interesting properties that we don't see in any of these other types of solid, like conductivity, malleability, ductility, luster. All of these metal specific properties happen because of these delocalized. Notice the electrons aren't stuck in one spot between two atoms. They're not localized, they're delocalized. They're non-directional because the electrons can move, ebb and flow. They're not only moving in one direction, but it's still a covalent bond here. Okay, and then we have a network solid, like different forms of carbon, like graphite or diamond. Also quartz, silicon dioxide, which is quartz. These have, quartz is unusual because it has atoms at the point in the lattice, but those atoms are not all the same atom, right? So some of them are going to be silicon, some of them are going to be oxygen, and you get this whole huge structure that's built off of these. Now, these are going to undergo directional covalent bonds. So the electrons in here are locked into a very specific place. They're directional, they're localized, and these bonds, unlike a molecular solids bond, these bonds tend to be very, very strong. Diamond is one of the strongest strongest crystalline solids that we know of, right? Same thing with quartz. It's extremely hard because of these strong directional covalent bonds. So in middle school, or even like beginning of high school, we like to say, oh, properties of ionic solids, properties of covalent solids. Ionic solids have strong bonds, covalent solids have weak bonds. Well, it's an unfair statement because you're generalizing covalent crystals, you're generalizing molecular solids and atomic solids, which include network and group 8 solids. You're putting them all into the same category and trying to give them one set of properties, and it just doesn't work because the bonding or the forces in between them are not equal. They're not all the same, and that's going to lead to different properties. Okay, now off of these types of solids, we want to talk about two applications that come out of this. And one of the applications we have already talked about, that would be alloys. You did a whole POGL packet on alloys, so consider this your review on alloys. Remember, there's two different types of alloys. There's a substitutional alloy and there's an interstitial alloy. So substitutional alloys are going to happen between atoms that have about the same atomic radius. The atomic radiuses are about equal. Substitutional alloys are going to happen between atoms that have very different atomic radii. But either way, when these metals are mixed or these nonmetals are mixed into metals, you're going to come out with something that kind of has properties of both. It has mixed properties, which can be very advantageous. Like steel comes out extremely strong and slightly rust resistant, which is better than iron, which tends to be weaker and more rust prone. So different types of alloys exist. You should be able to name them and kind of talk about what types of atoms would fit into each category. There's a example we'll do, a practice problem we'll do on that. Okay, and then the second application we haven't talked about, and this is semiconductors. Now, we kind of can talk about semiconductors now because we're talking about solids, and carbon and silicon both fall into the network atomic solid area. But we can also talk about semiconductors because now we've talked about molecular orbitals. So, and this is what makes something a semiconductor. Up until now, we've really classified things as it's either a conductor or it's a non-conductor. It's an insulator, right? So conductors tend to be metals. Insulators tend to be non-metals or nonmetal solids. But if we look at the molecular orbitals, we see why. So look at this table, look at this image here. A is going to be the molecular orbitals for diamond. And notice there's this huge energy gap between molecular orbitals for diamond. So if you are going to take some electrons from the filled molecular orbitals and you're going to move those electrons like a conductor would do, a conductor moves energy and electricity very easily, you actually have to get that electron up, way up here into the empty molecular orbitals. That's a lot of energy to overcome. If you look at B, B is representing the molecular orbitals for a metal. And notice there's no energy gap here. So electrons that are in these filled molecular orbitals can be promoted to the empty molecular orbitals super easily, right? Well, silicon is kind of the in-between. So silicon has an energy gap between its filled molecular orbitals and its empty molecular orbitals, but the energy gap isn't super big, and so electrons can be promoted under the right conditions. And so it makes it a semiconductor. Temperature makes a difference. Higher temperatures are going to lead to a better ability to excite these electrons into the empty molecular orbitals, and that will lead to more conduction. There is a term in here that's a decent vocab term, and that is conduction band. And a conduction band is just the empty molecular orbitals. That's what they mean by conduction band. So if there's a big energy gap between between the electrons and the conduction band, or the filled molecular orbitals and the empty molecular orbitals, if there's a big energy difference, it's going to tend to be an insulator. If there's a little energy difference, it's going to be a semiconductor, and if there's no energy difference, it's going to be a conductor. Okay, so silicon is a really good semiconductor, and then silicon can actually be doped to enhance its conductivity. So to dope a semiconductor means to introduce a new atom that changes its ability to conduct. So let me give you two examples of that. First of all, an N-type semiconductor is going to dope silicon or replace silicon by something like argon. And argon has one more valence electron than silicon. So it's going to have these extra electrons that are available to promote into the conduction bands or promote into these empty molecular orbitals. You can also have a p-type conductor, and a p-type conductor is going to dope silicon or replace silicon with something like boron, and boron actually has one less valence electron than silicon. So what that does is it leaves a hole in the lattice, a hole that an electron can fill. And when the electron fills that hole, it leaves another hole. And when an electron fills that hole, it leaves another hole. And so as electrons fill the holes, it actually leaves this moving trail of holes throughout the semiconductor. And so in the first case, you get electrons that are moving through the lattice. In the second case, you actually get holes that are moving through the lattice. It's a p-type conductor. P is for positive because the hole is a place where there is not an electron. So it's considered a positive hole. And you can see the N-type versus p-type conductor down here. A would be an N-type conductor with extra electrons to travel. B would be a p-type conductor that has holes open that electrons can travel and fill those holes. And oftentimes the N-type and p-type are actually brought together in a conductor to form a band. And depending on how you bring those together, that band can serve a couple different purposes. But that's kind of the gist of it, the gist of the N-type versus P-type semiconductors. And then you see that this semiconductor is in the form of a lattice, and that would be a network solid lattice because it has atoms at each point in the network. Okay, lots of information for you. We'll come back together and do practice in class with some of this information. Jot down your questions. Let me know what those questions are, and I will see you in class.